So what we'll do here is we'll have 1 minute per person, lightning talks to ignite your curiosity about the amazing set of posters that is about to follow. We have a great session this afternoon with anything from hardware and antenna design to using active transmitting bands for scientific use, to enabling coexistence between Earth and space. So stay tuned for the speakers. And we have our first one, AJ. Hopefully you're online. So for the speakers, please, when your turn comes, if you can, turn on your camera and speak. You'll have exactly 1 minute, upon which I'll interrupt you if you're not done, but I'll be nice about it. All right, AJ, take it away.
Hi everyone, my name is AJ Cuddeback. I'm a PhD student at CU Boulder, working with Dr. Palo, and I'll be talking about working towards using 5G millimeter wave cellular technology to do precipitation measurements. So we talk a lot in SpectrumX about how 5G millimeter wave might be causing interference with weather satellites, but it also has the potential to supplement weather sensing because of the fact that it operates at the frequencies that we use to measure water vapor. So I'll be talking a little bit about prior work that people have done using these frequencies and commercial technologies to measure precipitation, as well as looking at a little bit of prior work in using commercial user equipment and measurements from user equipment, talking about some of the challenges associated with these types of measurements, and then talking about the opportunities that we might have utilizing this data.
Awesome. I'm right on time. Thanks. Next we have Amy. Amy, are you on?
Yes, hi. I'm Amy. I'm an assistant professor at the University of Pittsburgh. We're still pretty early in our project, but it's investigating coordination mechanisms for future decentralized spectrum sharing regimes where we want to dynamically allocate spectrum slices based on user requests, but we expect this will be managed by servers deployed by different stakeholders, not a single centralized entity. So the challenge is that we need to coordinate between stakeholders that might be competing and not completely trust each other, with servers that might have different views of the physical state because of different measurements, might fail, and might even suffer security breaches. So we're mapping this problem to Byzantine fault-tolerant coordination mechanisms that assume a fraction of the servers can behave in arbitrary or even malicious ways and guarantee correctness despite that. So we've developed 3 initial models for that, and we're analyzing trade-offs between them. And if you're interested in learning more about what those look like, you can come see our posters.
Awesome. Thank you. Arvin, you're up next.
Hi, I'm working with Professor Al at CU Boulder. My poster is on my graduate work on the development of a V-band spectrometer. It's based on a new radiometry technique called multipath cross-correlation radiometry. This technique combines essentially known and unknown signals to generate multiple output signals, which are then amplified and cross-correlated. This technique gives rise to more equations than unknowns, thereby eliminating the need for any calibration views and is continuously calibrating or self-calibrating. The inversion equation yielding the antenna temperature does not contain any amplifier gain terms, and hence any gain fluctuations or gain compression due to RFI is inconsequential in this technique. We developed a prototype MXR instrument which has 2 paths, field tested it, and successfully retrieved brightness temperature spectra from 51 to 55 gigahertz. This instrument's digital backend enables the use of kurtosis-based RFI detection methods, and this is a key component in the demonstration of a spectrum broker concept for reporting any possible RFI coming from second harmonic emissions of 5G N258 and N257 bands.
Great. Thank you so much. All right.
Yes. Hi, my name is Ahmed. I'm a postdoc at University of Notre Dame. Actually, our work is to generate a 3GPP specific based open source simulator that is able to calculate the ERP 3D basically from a 5G base station. We know that 3GPP specifications are very wide, and most of them they are actually implementation dependent. So considering all of this wide range of parameters, our simulator mostly incorporates all of these parameters, and both we can introduce broad SSB-based beams, PMI-based beams, and calculate the average power in 3D space. Additionally to this, we are using real-world results measurements to evaluate the performance of our simulator. Thank you.
Right, excellent, and way to keep us on time. Arvind, you're
Hi.
up next.
Hi, I'm Arvind Aradhya, and I'm also a graduate student at CU Boulder, and I work with Professor Kevin Gifford and Professor Elliot Eichen in the Wireless Interdisciplinary Research Group. We're focused on different kind of coexistence approaches between passive and active users. So currently my focus is on trying to prevent interference to passive microwave radiometers that are orbital, so for the Earth exploration sensing system. And one of the mechanisms that we've come up with is to use the two-line elements that are published by the Space Situational Awareness providers to predict the path and the overflight of these passive radiometers over potential 5G base stations and other terrestrial interferers. And what we do is we compute the sensitivity of the beam pattern of the radiometer against the location on the Earth. And then basically that allows us to schedule and provide the communication provider with some information as to when they should cease transmissions. So come check out the poster in the demo.
Awesome. All right, I'm so impressed with all the timekeeping. Great. Bingyan, you're up.
Hi everyone, I'm Bingyan from University of Notre Dame. I work with Dr. Lenneman. My work looks at how to define spectrum efficiency for radar systems. We all know in communication systems, spectrum efficiency is defined by using Shannon's capacity. It tells us the minimum bandwidth needed to reliably transmit information at a given data rate. Radar instead estimates parameters like target's range or velocity. So in my work, I use the Kramer-Lohr bound to determine the minimum bandwidth theoretically required to achieve a target estimation accuracy. Then I define radar spectrum efficiency as the ratio between the ideal bandwidth and the actual bandwidth. Just so like Shannon gives us the best you can do with information, Kramer-Lohr bound gives the best you can do with estimation. So this makes radar and communication systems kind of comparable under a unified framework. Thank you.
Thank you. All right, excellent. Up next is Christopher.
Hello, everyone. My name is Christopher Wall, and I'm a graduate student at the University of Notre Dame also, but I'm under Professor Hochwald. Today, my poster's on sensor location selection via a maximum entropy heuristic for neural network-based radio occupancy mapping. So, of course, understanding the radio environment around us is important for the future of wireless technologies, from spectrum sharing to anomaly detection, you name it. And one way of estimating, as you just saw in the plenary talk, is to fuse these spectrum power measurements together in order to estimate the radio map over some region of interest. And of course, the radio map estimation is affected by where you place your sensors down. And thus, our goal was to try and find efficient spectrum sensor locations for the estimation. Well-placed sensors not only allow for more accurate radio map estimation, but can also lower costs of sensing by lowering the number you might need for a certain performance threshold. So in this work, we propose using a maximum entropy heuristic on the spectrum power measurements for selecting sensor locations in a region of interest. And this approach is fast to run and provide sensor locations and improve our estimation performance.
Great, thanks. All right, up next is Federico.
Yes. Can you hear me? Yeah.
Great.
Okay. Yeah. Thank you, everyone, for the beautiful talks of research, and also to the other presenters of the posters. I'm sorry, I will not be able to come visit you, but this all seemed very cool. So as we've been seeing today, basically spectrum is a scarce resource, and expanding access, especially to adjacent band, is key to unlocking more value. But scientific users from time to time may, for example, like radio telescopes, may face from commercial activity, and they can be paid off to tolerate it. So these make traditional market approaches unworkable. So the research question that we address is how can we design a fair, efficient sharing protocol when both the harm from the interference and the value of access are privately known? So basically, we propose a simple mechanism where the commercial user pays a fee and the regulator may inspect the scientific user's claim of the interference. So if the decision to share depends basically on two thresholds, one for low values of commercial users and one for high values of commercial users. And only in the middle, we do inspection. So basically, we show that these thresholds.
We're at time.
Okay. Yeah.
That all sounds amazing.
Yeah.
Make sure you visit Federico's poster.
Yeah.
All right. So up next, Joshua. All right. Joshua going once.
Hello, this session should be presented by Yiming Li. Can you hear me?
All right. Take it away.
Okay, thanks so much. So hi everyone, this is Yiming Li from Duke University. I'm first year PhD student advised by Professor Tinjun Chen. So I'm excited to share our recent work on a generalized deep learning model for signal coverage prediction in the CBRS band. So this work is actually built up on our previous dice-band paper, Geo2Sig map, where we introduce a deep learning model tailored for high fidelity signal mapping, prediction, and also how to efficiently generate a massive synthetic dataset using the real-world building information. So in this year's work, we actually enhanced the model generalizability to accommodate, diverse prediction error size. We also evaluate our model using over 20K measurement data points for a measurement campaign conducted by Professor Monisha Gauch's group. So our result shows the proposed model outperform all the baseline methods and achieve a more stable performance. So thanks so much, and I'm happy to discuss more in the following session.
Perfect. Thank you. All right, Margarita, you're up next.
Yes. Hello, my name is Margarita Blandon. I am PhD student in electrical engineering at the University of Puerto Rico. I am working with Dr. Rafael Rodriguez Solis. Today I'm presenting my research on broadband bow-tie antenna design and operate from 2 to 10 gigahertz. This type of the antenna can be used in many modern applications, such as radar communication system and sensing technologies. Welcome, my poster.
Perfect. All right. Up next, Nainesh.
Hey, hi everyone. My name is Nainesh. I'm a mechanical design graduate student at CU Boulder. I work under Dr. Laila Mazen and Dr. Zoya Povich, who also gave a research talk earlier. My work mostly focuses on designing the thermal management system and enclosure design for a 7 to 8 gigahertz portable phased array system, as the system encodes of a lot of high power boards such as the FPGA and MXFE, and you need to control their temperature so you get the exact efficiency. And overall, I'm working on enclosing this design into a Pelican case so it can be a portable system. I invite you all to visit my poster. Thank you.
Awesome. Thank you. I'd love to see that once it's enclosed and use it. All right, great. Next up, Ryan. Ryan, are you still here? Okay, so we'll move over to Sam. Samuel, are you here?
Hi, yeah. Can you hear me?
Yes.
Yeah. So hi everyone. My name is Samuel T. I'm a postdoc at the MIT Haystack Observatory. And I'm here to present you my work on the impact of mega constellations of satellites on radio astronomy. So I'm an astronomer, and I'm a bit worried about what would happen with all these satellites that are currently orbiting in low Earth orbit. And so I've been using one of the telescopes that we have here to try to monitor a bit some constellations, mainly Starlink for now. So I've been focusing on two axes mainly. So the observation of the satellites and also the modelization of the power that we would receive, taking TLEs and some link budget models. So I've developed some simulator that can give you different kind of scenarios, especially if you want to have some mitigation scenarios like a beam avoidance, where you want the satellite to turn off when it's passing through your bore site. So all these kind of things I've been able to simulate, and I'm focusing right now on trying to get the out of band, so a protected band in radio astronomy, protected band. If we can see the satellites, if there is some RFI that we can see, how much we can see from them. And yeah, if you want to talk about radio astronomy, I'd be happy to receive you at my post there for sure.
All right. I've learned a lot, so I highly recommend. Okay, I think Ryan is back. So Ryan, please take it away. Ryan?
Sorry, I'm here.
That's perfect.
Been having some computer issues. So I'm a master's student at University of Colorado Boulder, and I'm working under Dr. Zoya Popovic and Lila Morzal on frequency converters for a 16-channel digitally steered phase array. So we have a data converter board that works between 2.5 to 3.5 gigahertz, and it has 16 transmit channels and 16 receive channels. And we need to convert that to our antenna operating frequency between 7 to 8.4 gigahertz. So I've been trying to work on a up converter and down converter board that can maintain those digitally defined phase relationships and convert them to convert between the data converter and antenna operating ranges. So the challenges of that are maintaining the drive power for the mixers for minimum conversion loss and maintaining those phase relationships as you split a single LO out to drive multiple mixers. And yeah, if you want to know more, come see the poster.
Awesome. All right. And I don't think Aditya is here. But Aditya, if you're on, please speak up. If not, that was our round of lightning talks.